Hello everyone, welcome to our Beyond Number 8 webinar, Discover the Hidden Hazard of Shallow Groundwater. My name is Joanna Lee, the Marketing and Events Advisor at Agritech. Thank you for joining us today. Shallow groundwater is often an out-of-sight, out-of-mind resource, but it has a significant impact on our communities, infrastructure, and the environment. Today we have Dr. Helen Rutter joining us. Helen is a renowned hydrogeologist with over 30 years of experience. In today's session, Helen will discuss current issues and challenges related to shallow groundwater. She will provide practical insights and knowledge, which are key to making informed planning decisions and managing flood events. Before we dive in, I'd like to quickly remind you that this webinar is being recorded, and we have a Q&A session after Helen's presentation. Feel free to send your questions through the chat box throughout the webinar. Helen will give you good answers later. Now let's welcome Dr. Helen Rutter. Helen, the stage is yours.
Good afternoon. Welcome everyone. Thank you for coming along. Sorry, there's one or two small technical hitches at the start there, so hopefully we've sorted all out now. And I'll just share my screen. And hopefully you can all see the front page then. So yeah, as I said, welcome. Today I'm going to be talking about a variety of things that are all interconnected. So the title is Unintended Consequences, Groundwater, Climate Change, and Development, and Improving Infrastructure. And it's going to be a little bit of a, in some ways, a little bit of a random journey, touching on various things, but hopefully it'll all make sense. When I sat down and started writing the presentation, I did feel a bit like this poor guy sat on a pipe holding a pint of beer. It starts in one place and it wanders around, and then at some points you'll probably wonder what direction I'm going to go next. But ultimately, I'm hoping that what we're going to do is start to understand a complex problem. I'm not going to find any solutions today, but hopefully I can help understand what's quite a complex problem. And at the end of the day, hopefully we'll get to the point where we're starting to find some solutions. So as I said, the talk is going to be about shallow groundwater, about interaction with stormwater particularly, but also other infrastructure, what happens in urban areas, think a little bit about sponge city concepts, and also think about what might happen under climate change. And ultimately, it's all connected. So for those who are not familiar with groundwater, in my opinion, surface water is easy. I've still no idea what this guy is doing, but obviously you can actually see and physically hold and touch surface water. Groundwater tends to be more out of sight, out of mind. And many years ago, it's about 200 years ago now, there was a court case in America where the judge actually made this quote, which was basically saying that groundwater is so difficult to understand and so uncertain that it's absolutely useless trying to apply any rules to it. I think we moved on a long way from there, but we've still got a lot of uncertainties. It's still concealed and it's still largely unknown. So shallow groundwater in particular, it's basically just water that's in the sediments under the ground that's quite close to the surface. And the problem is it can emerge at the surface or it can cause problems in the subsurface. It's poorly understood in space and in time, and that's partly because it's not a resource. There's an awful lot of work that goes into investigating groundwater as a resource, but until very recently, no one was really looking at it as a hazard. However, groundwater really can hang around, and the photo at the bottom there shows a lane. It was actually in the UK that was flooded for about 3 or 4 months due to groundwater, and there's nothing anyone could do. It was inaccessible, and everyone who lived in the village at the end of that lane had to take the long route round. But that's how long it can actually hang around at the surface. And why is it a concern to us? It's really because New Zealand's got a load of coastal settlements on low-lying land, and a lot of these areas are actually going to be vulnerable to shallow groundwater as a hazard. How do you actually monitor shallow groundwater? Most of you probably be familiar with this, but I'll just using Christchurch as an example, and also because I'm going to be talking a little bit about Christchurch, this is quite relevant. We were unfortunate enough back in 2010, 2011 to be subjected to a few earthquakes. As a result of that, EQC put in a whole load of piezometers into the ground, and we had about 1,000 monitoring points across Christchurch at one point. And someone went around every month with a water level dipper and dipped the water levels and obtained the depth to water in all of these points. Back in 2016, EQC decided that was a bit too expensive, so they actually downgraded the size of the network to about 250 holes, and that's the slide on the right-hand side there. And within these 250 holes, they put down pressure transducers, which are monitoring groundwater levels at 15-minute intervals. So we suddenly get a whole load of very high resolution temporal data, but lower spatial resolution. And then from those holes, we get a lot of really, really interesting data. So I'll just talk about these quite briefly. From some of the hydrographs that I've shown here, you can see that groundwater varies both in the short and the longer term. In some cases, you can see very clear response to every rainfall event. You can see responses to rivers and tides. Groundwater also responds to things like dewatering, earthquakes, and lots of other things. In some cases, you start to see a seasonal response. So in the bottom left here, you can see how groundwater levels rise up in the winter due to recharge and then decline in the summer. And you get that year-on-year response where you've got an increase in groundwater levels in the winter, decrease in the summer. You can also see here the interannual response. So we happen to have a few dry winters over this period, and groundwater levels just declined year on year throughout that period. So the responses that we see actually tell us about what's driving groundwater behavior. So in this case, in the top right, you can see that it's very, very flashy. And what's happening there is that every time there's a rainfall event, groundwater responds and comes up to often close the surface and back down again. In the bottom right here, the orange trace shows a bore that is quite close to the coast. It's about 80 metres from the coast in Brighton. And that very, very noisy signal is actually the tidal response in that bore. The blue one there is actually about 280 metres from the coast. And you can see, but just within that short distance, you're almost losing almost all of that tidal signal. So that's just 3 examples of how variable the response can be across Christchurch. Antecedent conditions are really important. So this is just an example. In 2016, early 17, groundwater levels were at a pretty low level across a lot of Canterbury. Then we got Cyclone Debbie and Cook, which caused this response in April 2017. And that brought, and then further winter rainfall brought groundwater levels up to quite close to the surface. So they're about half a metre below surface there. Throughout July that year, it kept raining. And every single time it rained, groundwater levels came up to the surface and then declined again. The only reason there was such a problem during July was because already groundwater levels were up at half a metre below gravel. So every time it rained, it just pushed it up to ground level. If that rainfall had happened at a lower groundwater level, say, for example, in this period, it wouldn't have been a problem. So it's just to illustrate that antecedent conditions really are important. You've got to put groundwater levels into context, and you've got to have some care when you're looking at short-term data and or low-resolution data. So this period here was quite interesting. Groundwater levels rose up about a metre and then declined by about a metre in quite a short period of time. And we had a look, this occurred over quite a wide area, and we had a look at what was going on there. And we also looked at the timing, and this groundwater response here, that recovery, happened just before Christmas, and the drawdown happened just after New Year. And it turned out what was happening in this area was that they were doing a whole load of dewatering for laying some pipes, and basically switched the pumps off over Christmas and New Year and came back and started again. But this also illustrates just how important it is to look at the longer term picture. Because if you're looking just at this year here, then you'd think groundwater levels were probably about 2.5 metres down. If you actually look, once they've finished all the work and groundwater levels come back to normal, they're quite a lot higher. They're about half a metre to a metre higher than they would be during this period. The right-hand graph I always think is quite funny. This is showing the dip data. If you remember that when we originally had those 1,000 holes, someone went out every month and with a water level dipper and obtained water level measurements. So this early period here is that dip data. And then once sort of pressure transducer down the hole, we start to see the amount of variability that actually occurs in this hole, in this area. And I often sort of say, well, what does that tell us about the low resolution data, apart from the fact that whoever was going out and collecting the data didn't like going out when it was raining. I I'd just like to show one way we've used this high resolution data, because it's just quite fun to look at. A guy called John Haynes, who's ex-GNS, did some really clever work and basically interpolated all of the data spatially and then stacked it all together to create a movie. So the movie I'll show you basically is of this area of Christchurch. And basically, if the image is getting blue, then it means that groundwater levels are rising, it's getting wetter. If it's going more red, it's becoming drier. And we're just going to have a look at the period when cyclones Debbie and Cook moved across the city in early 2017. Hoping this works. Right. And you can just see how the groundwater sort of pulsing close to the sea. And then that was Cyclone Debbie coming across the city. Some areas sort of peak and then go down. Some areas peak and stay up. And then that's Cyclone Cook moving across the city. And this is just one way of visualizing this quite complex data where you can see where it's varying spatially and temporally. So I've talked a bit about collecting data and what it's showing, but what is the issue? There's lots of issues with shallow groundwater and lots of people really just don't appreciate it. First of all, there's a problem when groundwater effectively daylights or comes to the surface. And this top right photo here shows an example. The footpaths and the rest of the road are quite dry, but you've got this large area of standing water, which is quite likely to be groundwater. And I will caveat that with it's not always, sometimes it's a block drain, but in plenty of areas of Christchurch, that sort of scene is typical of groundwater. The issue is when it's actually raining and when you've got stormwater being generated. If the groundwater levels also rise to the surface, then the surface becomes an impermeable surface. So there's nowhere for infiltration to occur. And that can add then to the surface water flooding. Groundwater is really important in terms of liquefaction risk. It's one of the key risk factors. So again, if groundwater levels are high, the likelihood of getting liquefaction is much higher if we get an earthquake. It's an issue for dewatering. For infrastructure repairs, the cost of dewatering is, I was informed, about $1,000 a metre. So you're not going to have to be digging up too much pipework before you're going to be spending hundreds of thousands of dollars on dewatering. In some areas, that dewatering may be permanent for various reasons. You may have to keep groundwater down on a permanent basis, and that costs. One of the interesting things is that shallow groundwater causes issues with roading. So the areas of Christchurch that tend to be most hit with potholes tend to be those areas where we've got shallow groundwater, because the combination of vehicles driving over a road subbase with groundwater in it just causes damage to the roads. There's a big issue with infiltration into wastewater and stormwater. In Christchurch, it's estimated that possibly up to 50% of the water that arrives at the sewage treatment plant is actually groundwater that's infiltrated into the system. There can also be an issue with disposal of wastewater and stormwater. So areas that actually dispose of stormwater to ground, there may not be infiltration capacity. And the same with wastewater. There have been some horror stories of not being able to get rid of treated wastewater because of lack of infiltration capacity. On a human level, there's health consequences, because if you're sitting above shallow groundwater, houses often become damp. And another issue can be failure of planting. So lots of trees and plants don't actually like having wet roots. So there's lots of reasons to be concerned about shallow groundwater. So that's a bit about groundwater. Just to consider now, what's the effects of urban development? So within urban areas, obviously you've got more impermeable area, and that's going to generate more runoff, more stormwater when it rains. But on top of that, that's just the surface. Underneath the surface, you've got a water supply network, and leakage from that can contribute to groundwater. Wellington loses getting on for 50% of its water from its water supply network, and that's infiltrating into groundwater. Christchurch isn't quite so bad, but we're still losing about 25% of our drinking water to the pipes. Then you've got the wastewater system. The wastewater pipes are often the deepest. They often get inflow. As I said, about 50% of the water at Bromley in Christchurch is thought to be groundwater. They also get inflow from stormwater. Then we've got stormwater pipes as well. And there's two issues there. One is infiltration of water into the stormwater pipe network, and the other is actually areas where we're disposing of stormwater to the ground. So you can have infiltration or exfiltration from stormwater. Added to that, wherever you've got a pipe network, you've got this urban karst, and most people think of karst as being caves in limestone. This this concept of urban cast comes up when you start to look in the literature, and that's basically talking about the high permeability pathways that occur along pipes and trenches. And trenches are often filled with much more permeable material than the native ground. And so this pipe networks becomes just a really complex network of high permeability pathways where water and potential contaminants can move pretty quickly. So I've focused slightly more on stormwater in this talk. Obviously, urban areas generate stormwater, and it's disposed of by various means. And Christchurch has actually done a really good job of stormwater disposal, and thought very hard about which areas want to be, you want to have infiltration basins and which areas want to be wetlands in order to sort of manage this complex stormwater groundwater interaction. But basically water can be disposed of to streams, basins, swales, soakage pits, and it can increase or decrease recharge to groundwater. So often people think we've got all this impermeable area, so therefore there's going to be less recharge to groundwater. But there has been some work done that suggests that, especially where you're disposing of it to soakage basins or infiltration basins, you actually can increase recharge to groundwater overall. So we've talked a little bit about this already. How much does stormwater affect groundwater? It can cause groundwater mounding. On the other hand, how much does groundwater limit stormwater disposal? And that's affected by groundwater levels and the permeability of the ground. I won't talk about it much at the moment, but the cross-section sort of does give an indication about what could happen in some areas when the stormwater network actually gets overwhelmed. And this is likely to become an increasing problem with climate change, with sea level rise and extreme events. So I said I'd just touch on sponge city concepts. Sponge cities it's a relatively new concept that's used to describe urban areas that are designed to absorb or retain rain and prevent flooding. And it's a great idea. It originated in China. And there's lots of different ways of thinking about sponge cities, and it can be about having more parks, permeable pavements, gardens, infiltration and retention wells, urban gardens, green walls and roofs, that sort of thing. So the idea is to slow down that stormwater pulse when it occurs. What was interesting was that there was a recent study that showed Auckland actually came out on top in terms of sponge cities globally. So Auckland's doing a really good job of disposing of water into the ground, stormwater into the ground. But actually, after the Auckland floods, there were a few headlines going, "We need a sponge city to avoid future disasters." But you've got to take that into account in the context of the fact that they're already actually getting rid of a lot of stormwater to ground. And with sponge cities, I think the first thing is really understand the hydrology and hydrogeology before you start implementing some of the ideas, because you can end up with some unintended consequences. So moving on to climate change. So what might happen to stormwater and groundwater with climate change? There's been some recent work done, which was quite interesting, that suggested that more extreme, greater intensity and longer duration events could increase stormwater generation by up to 48%. And that's quite an increase, really. As a result of this, we're quite likely to get more groundwater recharge, particularly in areas that are disposing of stormwater to ground. And that's likely to be wanted at a time when you're already getting peaks in groundwater levels, because the groundwater levels are responding to those events. So this is where they all start to interact. On top of that, there's the potential for sea level rise. And this graphic on the right here shows the predicted increase in groundwater levels as a result of a 1 meter rise in sea level. And you can see how far inland some of those contours actually go. They tend to propagate up the rivers, because the rivers also are tidal, and it affects the sea level rise up them. And that work was actually carried out for the Christchurch City Council by Aqualink in 2020. So looking at this cross-section again in more detail, with pre-sea level rise, you've got the groundwater levels are reasonably deep. All the stormwater system and the wastewater system, for that matter, is just working reasonably efficiently. With sea level rise, so that's the red line, you can see that there are areas where groundwater actually rises into the lower topography areas, and you start to get groundwater daylighting. At the same time, some of these stormwater networks and wastewater networks are going to get overwhelmed by water infiltrating into them. And I'll just mention, it was actually a diagram that Simon Cox generated from GNS. So just talking a little bit more about the Christchurch example, as I said, Aqualink modeled the long-term effects of sea level rise in identified areas with shallow groundwater. Some of those effects actually propagated a long way inland. So some of the things that we did was, this is intersecting the wastewater network with the groundwater elevation surface. And you can see the areas are actually the areas of wastewater network where you're likely to have a lot of problems with groundwater inundation. So just doing simple exercises like this can actually help councils to think about where they might want to be concerned about things like infiltration into wastewater and stormwater networks. The diagram on the right is just showing areas that are predicted to have groundwater very close to the surface or at surface under 0.19 meters sea level rise scenario. So this was one of the scenarios that we did. Some of the work that Simon Cox has been doing in Dunedin has suggested that groundwater effects are going to be worse than coastal inundation in the relatively short term. So that actually gets a crossover point in about 20, 30 years' time when sea level in Dunedin actually gets the point that it's overtopping, when that effect becomes worse. But in the meantime, groundwater is going to increase and cause problems before then. All of this is based on a static surface, and if you remember back to those hydrographs we looked at really early on, you need to add to the static surface a dynamic response. And that dynamic response is, as I said earlier, going to depend on a number of things, including antecedent conditions, rainfall, and also the influence of the stormwater wastewater network, because that can actually act as a control. So I sort of talked about various different integrated things that possibly people haven't really been thinking about how interrelated they all are. But there's lots of unintended consequences of changes, what I'm trying to get to. So with the increased urbanization, you've got more stormwater generation, potentially more leakage from pipes, more infiltration into groundwater. So there's all of these things that are actually going to add to the shallow groundwater level. If you improve infrastructure, you can cause problems. So it reduces the opportunity for infiltration into infrastructure, and I'll cover that in a moment. And there's less opportunity then to drain groundwater. On the other hand, actually improving things like the water supply network would reduce the losses of water into groundwater and could have the opposite effect. With climate change, there's a very complex interrelationship between many factors. And I think one of the key things that councils have got to worry about really is the potential failure of infrastructure as groundwater levels rise. So just going through each of those in a little bit more detail. With increased urban area, we're going to get increased recharge and localized mounding, quite likely. There's going to be an increase in this urban cast. So the prediction of effects becomes increasingly difficult. So once you've got more pipe networks, more trenches across the city, trying to predict where groundwater is going to be a problem becomes even more difficult. There could be areas where urban development shouldn't occur, either because of existing or predicted future groundwater issues, or in some cases because you just can't get rid of things like stormwater. And as I mentioned earlier with sponge cities, before we start to put in lots of great ideas, just understand the hydrology first and think about how the groundwater is going to respond if you change the conditions. I mentioned earlier infrastructure repairs. As we try to improve our infrastructure, as I said, there's water supply pipes could mean that we've got less input into groundwater, but we've also potentially got a loss of groundwater drainage. And in this case here, what happened was the council sealed up a gravity sewer and put in a pressure sewer system, and overnight we got a change from groundwater levels that were bobbing around about half a metre below ground level. They rose roughly half a metre up to very close to ground level. So that's the effects of reducing that infiltration into a sewer in one area. With climate change, there's all sorts of things to think about. The sea level rise, changes in rainfall, that are then going to lead to changes in groundwater storage and groundwater levels. That thing about increased extreme events, you're going to get an increase in stormwater at the same time that you've got less ability to get rid of stormwater. Conversely, you're also quite likely to get some more drought periods at times, and so groundwater levels could decline. What might happen is you get more extreme seasonality in terms of the responses. It's a little bit of an unknown, and all of these factors are going to be going to be in combination with things like what happens with the infrastructure and how much drainage of groundwater is going into infrastructure. And so as I said, all of these are really interrelated and quite complex. I just wanted to mention Auckland in 2023. There was a global aquifer study that was carried out a few years ago, and that was looking at the implications of diverting stormwater to ground and the additional recharge that was caused there. And I've tried to track this down and tried to understand a bit more about the conclusions and not really got too far with it. But obviously it was a concern to Auckland even a few years ago. Then what happened in 2023 was that January, the wettest month on record, that was quickly followed by Cyclone Gabrielle in February 2023, and groundwater flooding occurred. And this hydrograph really shows just how extreme those events were. So this is a long-term hydrograph going back to 2016. And you can see what happened in 2023. And just zooming in on that peak, you can see how the Auckland anniversary rainfall caused one peak, and it was actually recessing when we got Cyclone Gabrielle causing the second peak. The flooding, groundwater flooding, persisted beyond the period of surface water flooding, and as a result, Aqualink were asked to model this by Auckland, and this is one of the models that they generated. And one of the interesting things was that the groundwater levels in red dots actually reduced a long time before the modelled responses were expected in blue. And this is a bit of a curiosity, and I've talked with Auckland about it, and we debated about whether or not it was due to the fact that once the actual surface water flooding had occurred and the stormwater had been disposed of, then the stormwater system acted to drain groundwater. And it's one of those things that really could do with a bit more sort of thinking about and working out whether that was the case. But when we're talking about dealing with stormwater through sponge city concepts, one of the quotes I got back from Auckland in one casual conversation was, "Isn't the city already spongy enough?" And possibly it is. It's one of those things you have to consider when thinking about stormwater and disposing of it in a case like this. So in terms of just wrapping it all up, I think what is desperately needed is to understand all of these issues combined. So we need to understand the depth of groundwater, how it varies spatially, how it varies with time, both in the short term from things like from extreme events, and longer term from sea level rise. We also need to understand these what are called non-linear responses. So this is just a diagram from Amandine Bossarell's paper. Non-linear responses are really talking about the fact that whilst groundwater levels are low, you could be getting things like exfiltration from wastewater and stormwater pipes into groundwater. But as groundwater levels rise, the opposite is going to occur. So they might actually be acting to control the extent to which groundwater can rise until we go in and repair them, and then they're no longer groundwater drain. But I think we really need to model and predict how things are going to change, both with increasing urbanisation. So things like increased impermeable surfaces, disposal to ground, increased urban costs, and improvements to infrastructure, and with climate change. And all of this is complicated by the fact that what we're actually looking at is groundwater in a really complex aquifer system anyway. If we can get there, I think we can make much more informed decisions about development. So really think about, if we're going to increase urban areas, where do we want to do it? Can we get rid of stormwater? Where are there going to be issues with shallow groundwater? We can understand better what are going to be the impacts as we get more extreme events. What are we going to have to think about? Where do we have to send pumps to deal with groundwater flooding? That sort of thing. And also understand the implications of changing things. So things like improving the infrastructure and spongifying cities. Just sort of are the areas that we may want to think very carefully about doing that sort of thing. So anyway, hopefully I've kept you all with me in that rather random walk through various things. Basically, shallow groundwater is poorly understood in space and time, and infrastructure really adds to the complexity. And we're going to get a much bigger problem with climate change. I really think that the interaction between stormwater and groundwater and other infrastructure needs to be better understood and allowed for in planning and development and thought about when improving infrastructure. And I think we've got to work with nature. We need a holistic view of the drivers of groundwater level change and the cascading effects from all of these things, but work with nature to find some solutions. And just as a sort of last point, just consider sponge city concepts in light of other factors. Sponge city concepts are great and absolutely need to be considered, but just be careful where we implement them to make sure that we don't end up with unanticipated consequences. Thank you.
Thank you very much, Helen. That's Q&A session. So, is there any questions? I saw one question from Jeff Brown online. Asked what contaminants are in Christchurch groundwater and the levels.
What contaminants are in groundwater? We've been debating this, and this is sort of one step beyond looking at groundwater levels, is actually understanding those contaminants, because we've got a huge number of contaminated sites across the city. So we've got PFAS, so the forever chemicals. We've got things like ammonium leaching from old historic landfill sites. There's all sorts of issues like that, which are likely to become more of an issue if groundwater levels rise. And that has been studied overseas. There's some work that was done in the UK by David MacDonald, looking at the impacts of groundwater level rise and groundwater flooding on landfill leachate, moving, and particularly ammonium moving away from landfills. So that's there are some real key issues with regard to potential contaminants, but that's even further off the radar than the whole issue of groundwater flooding in general.
Thank you. The next one from Mu. In the provinces, do they manage groundwater in the freshwater management plan?
In the what? Sorry, in the
provinces, do they manage groundwater in the freshwater management plan?
I think groundwater is managed by regional councils through regional plans, but this is where it's out of sight, out of mind somewhat. One of the issues, certainly until recent years, has been that the regional councils have focused very much on groundwater as a resource and not as a hazard. And then the civil defence and hazards people have tended to think about surface water and coastal issues, but not about groundwater. So groundwater has always fallen between the cracks. And it isn't, as far as I'm aware, it's not really considered in regional planning when in terms of trying to manage it. I'm not sure if that answers the question, but it does seem to have fallen between the cracks for many people for many years, and it doesn't tend to get included in policy and plans.
Okay. The next one is from the same person. Did not say the issue come from big dairy farms affected to the groundwater. So I think was asking for is there any big dairy farm effective to the groundwater?
There'll certainly be impacts of farming on groundwater quality. I've focused today really more on the urban areas where that issue with farming and contaminants from farming isn't so much of an issue. But if you're thinking about the impacts of things like irrigated farming on groundwater levels, then there's a couple of issues. One is a lot of irrigation relies on abstracting groundwater, so that keeps groundwater levels down. But then by irrigating, you're keeping soil moisture deficits low, so when it does rain, you get more groundwater recharge. So that's a whole other issue, really, and it is really complicated. But it's not so much of an issue when we're looking at urban groundwater.
Yeah. As another question from the same person. How much do we understand the groundwater, not just shallow groundwater, aquifers and aquitect?
That will vary very much on the area that you go to. Some areas are very, very well characterised. The Christchurch or the Canterbury Plains, for example, have got so many observation points, and there's been a whole load of work done. There's been a whole load of modelling, massive amounts of investigation. So that sort of area reasonably well characterised. There will always be uncertainties. We can never get away from that. Like I said, it's not easily observable. So there are always uncertainties, but some areas will have a huge amount of work carried out, and we'll have a reasonable handle in terms of understanding them. There are the other areas where there's next to nothing has been done, and if we're thinking about things like groundwater flooding, South Dunedin, for example, when Simon Cox started working down there, had no measurements at all. So you're starting from scratch. You have to start thinking about where am I going to put boreholes down to observe what's happening, and then eventually you start to gather data, and then you start to be able to use models to predict what's going to happen under different situations. But it will vary very much from area to area.
Okay. Is there any other questions from any other ones? You can ask questions directly to Helen and just unmute yourself. Comes another one online. Many places in rural areas equally nitrate in groundwater come from big dairy farms and fertilizer. Fresh water includes surface and groundwater. Cannot manage fresh water if not included.
Yeah,
Actually,
absolutely. Yeah, no, absolutely, and that's the focus of most of the regional plans these days, and the MPS for fresh water. It's about trying to manage those and yeah, trying to reduce inputs into the environment and reduce the adverse impacts of those sorts of things. But yeah, that's another that's a whole other topic.
Oh, we have another new question from Carl. Are you aware of any work on the effects of compaction on surface sorry.
Infiltration, yeah.
Yes, sorry.
Yeah. I am aware of some work that has been done. It's in Auckland by Robin and I've forgotten, Simmons, I think it is. And she's certainly been looking at what's the impacts when you actually create a development. You obviously, there's all the works that's going on, there's a lot of compaction of soils, and you can reduce infiltration capacity in those areas. So she's been doing some work investigating what needs to be done to increase infiltration capacity. So that's a conversation I want to have with her sometime in the near future, because in some ways I think we both need to understand each other's points of view. I mean, I'm talking about not encouraging too much infiltration because of the adverse consequences, whereas Robin's talking about increasing infiltration to get rid of surface water ponding and things like that. So I think this is where it's really, really complex, and we all need to understand different points of view and understand the implications of work that's going on. But yeah, I mean, if you want to if you get in touch with Carl, I can give you some details about the work that has been done up there.
Any more questions? Okay, I might have a question from myself. What methods are most effective for the long-term monitoring of shallow groundwater levels and quality?
What methods are most effective? I mean, traditionally we've totally relied on holes in the ground and piezometers, which is great because we can get some really good high resolution data at those sites. But the problem is what happens in between monitored points. And the work that we did a while ago for the Christchurch City Council suggests that once you move more than a few hundred meters away from a point, there's very little confidence in understanding where shallow groundwater is. And I think it's partly because of this urban infrastructure issue that there's so many things affecting shallow groundwater that unless you're close to a monitoring point, you can't have a great deal of confidence about it. We are pulling together a research idea to try and use some innovative approaches to mapping shallow groundwater and integrating that with that high resolution temporal data. But I mean, you can see from that movie that I showed earlier on just how complicated it is, how complicated the response is to rainfall events across the city. And there's so many things to be factored in, it gets really difficult. But yeah, I mean, we rely very much on piezometers and pressure transducers and recording the response directly at a point. And I think the big missing gap is what happens in between those points.
Yeah. Thank you very much. Last chance for people asking questions, if there are any. Okay.
I'm always very happy to continue the conversation if anyone wants to get in touch and have a chat later.
Yeah. It comes another. Oh, it's great. Yeah, okay. Thank you. Okay, as it might come to the end of today's webinar. Helen, thank you very much for sharing your valuable expertise with us.
Thank you. I'm sorry about the technical hitch at the start.
It's okay, it happens. Thank you to all the attendees for your participation and great questions. We hope you found this session helpful and informative. If you have any further questions or need more discussion with Helen, please feel free to reach out via our website and social media channels. Welcome to follow us on Facebook and LinkedIn to receive updated news from us. Have a wonderful day, and we look forward to seeing you again at our next webinar. See you next time.
Thank you.
Thank you. Bye.
Bye.